Hi, ladies and gentlemen. Welcome to today's lesson. We're going to talk more about least squares and linear models. We'll do a little bit of comparison with nonlinear models near the end, just to have the conversation on what the difference is. Today's point of emphasis is really about understanding how broadly applicable the linear modeling game really is. We're going to go through, spiral back through several of the ideas that we talked about in Strang section 4.3 and just apply them to a little bit of a different situation. So, to start here, this is section 4.7 from my text, and it's just a single section on least squares, but it provides us with a little bit different perspective than what Strang provides. Again, a lot of his work is oriented more towards the foundation of linear algebra as opposed to higher and higher order applications. And we really want to make sure that we are stressing the applications when we're talking in Math 344. So this just starts out with an example. And what we have here are a set of data that comes from skiing on Copper Mountain. And what we have is number of skiers that show up on the mountain and the resulting number of leg injuries. And what we want to do in order to help out the people at Copper Mountain is we want to model the association between the number of skiers and the number of leg injuries. This is important for manning considerations. How many people do we need in the hospital given that we think there are going to be a certain number of skiers on the mountain? In order to come up with that, we need to model the data. So the data are presented down here. This is a graphical representation, and this really is always step zero for where we want to go. And we'll go through this idea, but really step zero, data. We need to have data, and we need to take our data and do whatever wrangling or cleansing that is required in order to set it up in a way that we can use it as the foundation for a model. So one thing that we could do, right, is we could just come up with a ninth degree polynomial that satisfies these 10 data points. That certainly is possible because a ninth order polynomial has 10 degrees of freedom. It has a constant and then it has a coefficient in front of each of the terms. So we could exactly fit the data. The problem is that generates a terrible model. Here's the model that we would get with a ninth order polynomial. We go through each data point exactly. We hit these data points exactly. But that's a bad idea. And we can obviously see here, right? The estimation from this model is if we have 7,500 skiers, we're going to have a negative 2,000 leg injuries. That makes no sense whatsoever. So just because we can exactly solve a problem doesn't mean that that's the appropriate thing to do. Again, we start with the data. We want to take a look at the data and we want to see what an appropriate model is. So in this case, we're going to start with a simple line. This is a spiral back through what we talked about last time. And we have a simple linear model right here. We have a constant and our linear term for the polynomial. Using the data, we set up 10 equations. So this gets really to steps 1 and 2, right? So step 0 is the data. That's where we always start. The next step is we're going to come up with a model. We want to make sure and write down the general form for our model. What is the model? For the case of linear models, what we're going to have is linear combination of basis functions, or really basis vectors, because as we know, we can think about functions as vectors in the vector space of functions. So this is a linear combination of basis functions. And as long as the way that we do this is as a linear combination, we can pick whatever basis functions we want. And we'll see that as we move forward. Right now, it's very simple. We have our most straightforward model, which has only two basis functions, 1 and t. And we are using those. We build these 10 equations. We have 2 degrees of freedom in our model. We have the constant term and the coefficient, and we have set up 10 equations. Obviously, there's no line that goes through these points. There is no solution to this problem. So we do everything that we talked about last time. We go in and we know the system is inconsistent, so we're going to left multiply by A transpose. Left multiplying by A transpose takes the right-hand side vector and eliminates the piece that is not in the column space of A. And it basically is going to end up doing a projection of the column space into the column space of A. And that's what we talked about last time. And the result of this is the least squares solution. So in my book, instead of using the X chevron that we've been talking about, remember Strang uses X hat. What I use is X least squares, and it is a vector. So this is analogous in our section here. So of course, we're going to solve the same minimization problem we did in section 4.3 of Strang. We are minimizing the difference between the B vector, the set of data vector, if you will, and our approximation for all possible X values. And the thing that minimizes this, of course, is the least squares solution. So this is what we're trying to do. The error vector, which we already know about, is the difference between our approximation and B. And so this really should be an X least squares here, right? The error vector, which Strang calls the E vector, and I'm okay with that, that's B minus A X least squares, right? Or the X chevron, if you will. And this is the thing that we are trying to minimize. When we minimize this vector's magnitude, then we have found the correct solution. And so then I walk through just a simple example here as a point of demonstration. And this is similar to the kind of thing that we talked about last time. So in this case, we have an A matrix with a column space, which is really just the x1, x3 plane. And we're looking for a solution that hits the vector 1, 1, 1. And so this is a graphic that goes with that. You can read through this. This just gives the visual in my textbook showing here's the B, and the projection of that B into the column space of A is right here. And then the error vector, of course, is in red. So you can look through that. Let's go back to the problem. We're going to solve this problem. We've changed the independent variable to something meaningful. So this is really step number 2. Once we have our model, we're going to set up the equations from the data. This is the idea of how we are doing this. So we look at the data, we can graph the data, we can get an idea of the kind of model we want. We select that model, and then we're going to apply the data to the model to come up with our set of equations. And that's what we have here. In this case, like I said, we have S for skiers as the independent variable. We always want to use meaningful variables whenever we're talking about application problems. We want to avoid the ridiculous X and Y. I know we're accustomed to using those things, but it's much easier to communicate what we're doing in modeling if we use meaningful variables. So once we have this set up, this is really going to be our A and our B. And now we know if we apply the transpose, we end up with something that looks like this. And now we have a 2x2 system that's easy to solve. We RREF this, and we end up finding the values of X naught and X1. So we have a typo in here. Sorry about this. This is X1. This is X naught. So those originally were A's, and then I shifted them over. So the least squares solution is this vector right here. And that's what we say right here. This is the least squares solution. This is the constant for our line, and then this is the slope. And this is a graph. It's always, again, because humans are visual, a good idea to graph your data and your model together so that you can get an idea of, hey, does this seem like a reasonable approximation? And of course, the answer is no, it's not a good approximation at all, but we didn't think a line would be a great approximation anyway. It didn't look like the data are necessarily linear. So a little bit more with respect to the calculations that we do once we have our model. We want to find the projection of B into the column space of A. That is the best approximation. So the best approximation that we can come up with is A multiplied times the least squares solution. And when we do that, we end up with an approximation to the data. This is what Strang refers to as the P vector. This is the projection into the column space of A. It's obviously from the column space of A because we built it by taking A times the least squares solution. The other thing that we can build is the error vector. And the error vector is the difference between the actual data and our projection. And remember, that is going to be a vector that is orthogonal. And what we're interested in is we're interested in a couple of things with this vector. One of them, of course, is the magnitude, because the magnitude of this vector is the least squares error. The other thing that we're oftentimes interested in is trying to locate where is the biggest discrepancy. Where is our model doing the worst job of predicting? And we can see here it's this last data point. This gap is larger than any of the other gaps along here with a 21.4. So, the graph tells us that we don't have a great model, and the error vector is also pointing in the direction of the fact that we don't really have a great model. The least squares error calculation is 38. That's the magnitude of the error vector here. And so what do? We change our model. We're going to improve. We're going to do what Strang talks about at the end of section 4.3, which is we're going to use a quadratic model. And the quadratic models here, I'm not going to walk through the details because you're familiar with this, but we set up our equations. We do everything that we normally would do. There's one point of note about using the quadratic model, and this is an important piece of understanding numerical stability. So what we have here, when we use the number of skiers and have our model built, is you notice we have a huge disconnect between the magnitudes of the largest and smallest values in A transpose A. This is a very common occurrence when we are solving these problems. So when we calculate A transpose A, we are amplifying the difference between the largest and smallest values that are in A. And in this case, once we start to approach anything where we have 14, 15, 16 digits of difference between these numbers, a modern double precision arithmetic computer is not going to give us a good answer. The difference between these two numbers in terms of magnitude is directly related to the accuracy of the result that we'll get. So if we have 8 orders of magnitude difference between the largest and smallest numbers in A transpose A, we will have given up 8 of our 16 digits of accuracy. And the best we can hope for is about 8 digits of accuracy in our solution. And maybe that's enough. In this case, the difference is about 16, which means we've given up all 16 digits of our accuracy. And we can't hope to come up with an accurate solution. So what we have to do then is we have to actually scale the system. This happens regularly. Transforming problems from the actual set of data that we have into things that we can solve is an integral part of using applied mathematics to help us solve problems. So easy enough, right? All we have to do is take the number of skiers here and divide by 1,000 so that the number of skiers is represented as thousands of skiers. And then the number 8,086 would become 8.086. And that would completely eliminate all of our scaling issues. So that's what I did in order to come up with this solution here. This provides us with, again, a least squares solution. So once we have our equations, then really what we're going to do is we're going to build our system, AX equals B, from the equations. And then we're going to apply A transpose A to both sides, which is what provides us with the projection, if you will, of B into the column space of A. And then we can RREF and solve the system of equations just like we always would. And the result of this is going to be the solution. So this is the RREF of A transpose A augmented with A transpose B. And that gives us our solution. Then we can, and really now we just keep working through the steps. right? Our best solution is A times the least squares. This is the projection vector. This is the same thing that Strang calls AX hat, or we've been calling it X chevron. Right? That is our best approximation. That is the projection of B into the column space of A. We can also find the error vector. The error vector is equal to the B vector minus the projection vector, which is our AX least squares. Right? And then the actual least squares error, right? So this is the least squares error is the magnitude of that vector. So all of those calculations are done here as an example. All right, let's talk a little bit about, and you'll notice the analysis here for the worst case. Let's talk a little bit about how broadly we can apply the ideas and the modeling that we've been using. Let me copy down this model here. So here's the model copied down. This is what we have right here. G of S is equal to x3e to the 1/10,000th times s plus x2 s squared plus x1s plus x naught. These are the basis functions that we're using. We still have a linear model because we have taken a linear combination of these four basis functions. What is a nonlinear model is if we did the following. So in this situation, we have a nonlinear model because we have one of the coefficients that we're looking for, in this case x4, that appears in a nonlinear way. This is not just a coefficient of part of the linear combination. We are trying to decide here what the growth rate is of our model. We can't do that using a linear model. This makes it nonlinear. It would be the same as if we had picked a sine function and we didn't know what we wanted for the frequency of the sine function. This is not a coefficient out in front of the sine. This is not a function that is part of the basis. It's a function, if you will, that is changing. So if we want to use a sine or an exponential or something that has a parameter like frequency or growth rate or one of these things, we need to analyze the data to come up with a good approximation of what that frequency would be, or what that phase shift, or what that growth rate or decay rate would be. We can't use a linear model in order to find what these parameters are going to be. In order to do that, we would have to use nonlinear curve fitting. Not a topic that we discuss in this course because we're focused on linearity. So what we want to do then is say, how do we set this up? How do we proceed with this? And the idea is exactly the same. It's not written out here. It's a good exercise for you to go through it. The resulting graph is found here, but it's the same as what we've done before. We looked at the data. We think this is a good model. We have written down our model, and we're going to apply the data to come up with the equations. Once we have the equations, we're going to write those equations in matrix vector form, AX equals B, and then we're going to left multiply by A transpose. And that's going to give us a system that we can solve for the least squares solution. Once we have the least squares solution, we have everything. We have the projection of B into the column space of A. We have the error vector. We have the least squares error. We can determine where the worst approximation is across the entire range of inputs. All of that information is available to us. All right, so what we're going to do is, these are 4 of the homework problems. We also have a handout that's going to provide us with some additional problems to do in class. You are, in preparation for the participation questions, you are going to complete 3 of these problems. You're going to complete problems 1, 3, and 5. And all I want to do is just walk through a little bit about how you want to go about this. So you have the data. You want to put those into MATLAB. So you want to take this set of data and put it in and make a matrix out of it. Then what you're going to do, that's step 0. Step 0 is always the data. Plot it, look at it, see what would be a good model. We're going to start with some simple models just as a point of review and just to get the flow down to make sure we're going through all the steps appropriately. So the first thing we're going to do is select our model, which has been provided. You might find a better model once you graph the data. Right? Then we are going to go through and we are going to set up the equations, which we know are going to be inconsistent. Then we left multiply, and we have something that we can solve. So determining the solution, which is really, and this is an extremely important point that often gets overlooked, this is the purpose of writing down the model. The least squares solution is nothing more than the coefficients. Right? When we solve the least squares solution, we are finding the values of the coefficients of our model. That's what the least squares solution is. So here we have the least squares solution, which allows us to funnel right back into the model and complete our model. Now we have the model, we have the ability to graph the model. We have the ability to directly compare it against the data. We have all of that. Once we have the model, we're going to find the projection vector, which is our best approximation. We're going to find the error vector. We're going to find the least squares error, which is the magnitude of our error vector. And then we're going to find where we have our worst estimate by looking at the error vector itself and figure out where its largest value is in absolute value. And then finally graph the data and the model. And that'll be done again in MATLAB. And it's nothing difficult, right? We can just set up a plot vector and use the linspace command like we always do. And once we have that, then it's a simple plot of the plot vector, which is our set of inputs, and then our model, which would be f at the plot vector. And remember, we're going to define f in MATLAB using the at function. So this would just be a simple at t, and then we plug in whatever our coefficients in model right here happen to be. So just as point of review, these three problems, 1, 3, and 5, those are the preparation problems. They're also homework problems. So you're getting 2 for 1 working through these problems. Do them in your MATLAB script, and once you have the flow correct, you'll see from after the first one, and really you're just going to tie back into the stuff that you've done from section 4.3 in Strang. All you have to do then is just change the model. When you change the model, that's going to change the A matrix. Once you change the A matrix, then the flow goes exactly the same. Thanks very much, and we'll see you in class.